Hello everyone, welcome to physics. This is our next lecture. We're talking about motion, and I'm putting the question to you right now. What is motion? How do you describe it? How do you know what's happening? And if you pause the video right now for like the next minute and kind of brainstorm a couple topics, so just go ahead and do that. Pause the video, right? Have you paused it yet? Okay, good. You're back. Now, if we want to talk about motion, the most common things that people end up talking about is, well, they talk about distance traveled. People may talk about length traveled. People talk about time. And if you kind of simplify these down, and there's more, I'm by no means is this a complete list. You end up with two things that are the most basic representations: distance and time. Those two terms can completely describe any type of motion. Right? So that's going to be the basis of this class. Well, we might as well start about, we talked about this last week, we talked about vectors. We know that speed and velocity are technically two different things. So let's start talking about speed first. So we can write this out as a word problem. We can say speed is the distance something travels over a period of time, and or we could write it as an equation, which is the most common one to do. You can even, you don't have to use words to write this as an equation. You could abbreviate it as speed equals distance over time, and I'm sure this is something you've seen before somewhere. We know the difference between speed and velocity. Speed is a scalar quantity. It only has a magnitude, whereas velocity has a direction associated with it. So if you want to convert this into a velocity equation, we know velocity is a vector. There's our little hat. And well, which part of this do you think is going to be a vector? In order to get a vector, you know it has to have distance and time in it somehow. That means one of these things has to be a vector quantity. And we're pretty sure time is not. So guess what? It's the distance part. Do you remember the vector form of distance? Good for you. It's displacement. And I happen to use the exact same variable d. Some books, some people use s, some people use all kinds of crazy letters. It's d for displacement. Now, for our purposes right now, speed and velocity are going to be talked about interchangeably, okay? It's easier at this stage of the game to talk about and to substitute distance for displacement and make our discussion a little bit easier. So here's my next statement. Let's say I walk 1 meter every second. How fast am I going? Can you translate this from a sentence into a value? I walk 1 meter every second. We can assume that the person is talking about a constant motion. They're doing this every second. They're walking 1 meter. Well, sure, why not plug it into the equation? I have a distance of 1 meter. I'm doing it every 1 second. So I end up with a unit of value of 1 meter per second for speed. So that's it really is as simple as that, okay? Okay, so here's an example problem. What is the average speed of a car that travels a distance of 750.0 meters in 25.0 seconds? Yes, the decimals are important. Well, plug it into the equation. 750.0, and you don't have to write the units in there. A lot of the problems we're going to get to, the units can be a little bit complicated if you throw them in, and that's over 25.0 seconds. And if you remember your rules of significant figures, yes, they are important. This number has 4 sig figs, this number has 3. And the multiplication division rule says your answer can only have as many sig figs as the value with the least. So this one has 3, which means your answer can only have 3. And if you do this little multiplication process, yeah, right, that's not multiplication, it's the opposite. Division process, you get an answer of 30.0 meters per second. Now, the sig figs are important, and I'm not going to stress too much on them right now, but they will be important. Um, well, here's the deal. We said something very specific here. We said average speed of a car that travels 750 meters in 25 seconds. Do you think this car was traveling exactly 30 meters per second the entire 25 seconds? Do you think they might have changed their speed a little bit? Maybe they saw a state trooper and they had to slow down a little bit. Maybe they were speeding up to trying to pass a car. Okay, do you ever think about that? So why average speed? So what I've done is loaded a graph. This is a common graph you see in a lot of textbooks, and this represents telling you how long it took. It took you 120 miles. You went 120 miles over in 2.4 hours, 140 miles over 2.6 hours in this leg. Do you really think you went one specific speed this entire trip, or do you think you had many, many speeds? So what we're really looking at here is a great graph that represents a concept of average speed or average velocity. Now, look, most of the velocities you're going to be calculating this year are in fact going to be average velocities. Only once in a while, and be very specific about the times where I actually ask for what your velocity is right now or your instantaneous velocity. There's going to be a brief lecture talking about instantaneous velocity, but we'll get to that another time. Suffice to say, average speed pops up a lot, but we end up just calling it, oh, what's the speed? Okay, just be prepared for that. Well, if speed is simply the distance traveled as a function of time, what's acceleration? Okay, what does acceleration actually describe? Well, unfortunately, a lot of people think acceleration and speed are kind of the same thing. Oh, somebody just sent me a text message. Um, Acceleration and speed are not the same thing. And I have a little definition I'll put up here for you. Acceleration is something which describes how your speed or velocity is changing. It only describes the change in your speed or velocity. It doesn't care how fast you're going or how fast you were going. It's only talking about the change in the event. Now, this is a concept which is a little bit unfamiliar to people. So what we're looking at here, if we talk about this, we're talking about acceleration, which is a variable a, and it is a vector quantity, but for now, I'm not going to deal with the vectors. We'll leave it out. Acceleration is talking about the change in speed or velocity as a function of time. So delta S over delta T. Well, what kind of units might you get out of this? Well, speed has units of meters per second. It's a rate. And what's time have? Well, time has units of seconds. So what we're really looking at here is something very special. We're looking at something that is a rate of a rate. It's a rate of a rate. Now, the units for meters per second. I think we better do that by giving an example. So here's your example. Let's say I start with a speed of 0 and I accelerate, or I change my velocity at a rate of 1 meter per second What am I doing? So we can think about this. I'm starting with a starting with a speed of 0, and it says every second, this is the per second, that's what that means. Every second, I change my speed by 1 meter per second. So if I'm talking about a timeline here where the distance between this point and this point is 1 second, in 1 second I will now have a new speed of 1 meter per second. In another second, I'll have a speed of 2 meters per second, and then 3 meters per second, and then 4 meters per second, and so on and so on and so on. So the time interval between here and here is exactly 1 second. The time interval between here and here is exactly 1 second, and so on and so forth through the rest of these. How does that contrast to someone, let's say, moving with a constant speed of 1 meter per second? Person moving with a constant speed of 1 meter per second is going to be moving 1 meter per second here, and here, and here, and here, and here, and so on. Their speed does not change, versus the person who is changing their speed. Now, it's important to note, is acceleration only dealing with an increase in speed, or can it also talk about a decrease in speed? Well, the answer is both. We can talk about a positive acceleration or a negative acceleration. That's how a physicist would describe it. Or what you may be more familiar with, we can talk about an acceleration and a deceleration. Okay? Let's go a little bit more into the units. Okay, when I first start talking about acceleration, I like to write it in terms of very, very specific units. So let's say I have an acceleration of 1 meter per second. I literally write this as 1 meter per second. And that means exactly what we had up here before. It means every second I travel, I'm going to get faster by 1 meter per second. Okay, I like to write the unit like this because I think it implies more meaning to a new student. Traditionally, however, this unit is defined like this. acceleration is defined as a meter per second divided by a second. Now, if you had that in math class, your teacher would yell at you. So you know that this fraction in the denominator here goes into the denominator down here, and you end up with a meter per second times second. And again, if you left it like that, your math teacher would yell at you. So you know you have to change that to a meter per second squared. And this is the unit of acceleration. However, this has absolutely no meaning to me. I don't know what a 1 meter per second squared is. I do know what a meter per second is. So initially, we're going to be using this unit because I think it helps, again, I think it helps a new student. This unit we can use when we're a little bit more comfortable with this topic. Okay, so I wrote down the equation for acceleration. It's delta s over delta t, the change in speed as a function of time. And the delta notation you should know means final minus initial. It's always talking about the change. So we're talking about final speed minus initial speed over final time minus initial time. Whoops, screwed that one up. There we go. TF minus TI. The thing is, a lot of times in the problem, we start at 0 time. So the initial time is 0, which means this whole bottom part of the equation kind of changes just to get rid of that. It becomes T. So let's do a problem. Okay, so here's our problem. Notice I've changed the expression to get rid of the other time here. An Indy 500 race car increases velocity from 4 meters per second to 36 meters per second over a 4-second interval. What is the average acceleration? Again, this is something where it's average. We're assuming that a car can actually have multiple accelerations. You can try this in your own car. Step on the gas pedal a little bit versus stepping on the gas pedal medium versus a lot. You can actually change your rate of acceleration. So we're talking about average acceleration right now. Well, plugging this into this equation, what looks like we have a final speed of 36.0 minus an initial of 4.0, and it's divided by 4.0 seconds. Now, you remember your sig fig rules. We're talking about a subtraction process here. Subtraction rule is you're looking for the least number of decimal places, so this top part can only have one decimal place. So we're looking at an answer of 32.0 divided by 4.0. Now we use the multiplication division rule, and our answer can only have 2 sig figs, so we are looking at 8.0 meters per second as an answer. And that wraps up this lecture. This is just a brief introduction to speed and acceleration, some of the basic concepts of motion. In the next lecture, we're going to talk about graphing motion, which is really important. It's actually a whole special section on the AP exam just about graphing motion. And then we'll launch into a brief discussion of what instantaneous velocity means. And then we go into the kinematics equations, okay? Thank you very much for watching, and I'll see you in class later.